Welcome to another part of my step-by-step reinforcement learning tutorial with GEM and TensorFlow 2. I'll show you how to implement a reinforcement learning algorithm known as Proximal Policy Optimization for teaching an AI agent how to land a rocket, called LunarLander V2. By the end of this tutorial, you'll get an idea how to apply an on-policy learning method in an actor-critic framework in order to learn navigating a discrete game environment. And next, followed by this tutorial, I will create a similar tutorial with continuous environment. I'll show you what these terms mean in the context of the Proximal Policy Optimization algorithm, and also I'll implement them in Python with the help of TensorFlow 2. And here you can see the results of my implementation. Of course, I will actually say that I already done everything and I'll just cover this. And I'm not going to show you how I'm programming it live because such tutorials require a lot of debugging and checking where are mistakes, and anyway, it requires a lot of time. So first, you should start with the installation of our game environment. And I go to the original GEM GitHub page, and here is written that we should do a pip install GEM all. And pip install, I don't see here, but we need to do a pip install box2d py. Let's see, box2d, maybe it's only written here. So this is required, but on Linux it's quite easy to install it. On Windows it's a little bit more complicated. You might need more compilation installation related with C and so on. Doesn't matter, you should Google, it's not related with this tutorial. If you face some problems with the installation, you can find all the detailed instructions on this GitHub page. Anyway, I'll give a link on my text version tutorial. Note that code for this and my entire reinforcement learning tutorial series is available on a GitHub repository. And here is the link. Of course, I'll add everything in the description. I'm using the OpenAI game environment for this tutorial, but you can use any game environment. Just make sure it supports OpenAI GEM API in Python. And of course, you can adapt this not to GEM environment. You can create your own, and I'll show you this later in future tutorials where I'll be making a stock trading environment for automated reinforcement learning trading bot. And anyway, you'll see this in future. If you would like to adapt code for other environments, you just make sure your inputs and outputs are correct. And now, if you clone my GitHub repository, now install the system dependencies and Python packages required for this project. Make sure you select the correct CPU, GPU version of TensorFlow appropriate for your system. And you should simply use a pip install -r and your requirements. Anyway, you should probably install all these libraries in the requirements txt folder. Now I suppose we have installed our environment, and now we have installed everything. Let's try to test whether it runs correctly on our system or not. So here I have a random code. It will be posted on my text version tutorial. I have it on Gist anyway. And now I have here everything I need. I'll copy this copy and I'll write a code to my random code. Let me see. It's temporary, I'll remove it later. So I'll run this as random. First, a typical reinforcement learning setup works by having an AI agent interacting with our environment. The agent observes the current state, and this will be our current state. I just call it next state of our environment, and based on the some policy makes the decision to make a particular action. And right now we make this particular action by randomly, and this action is then relayed back to the environment, which moves forward by one step. this generates a reward which indicates whether the action taken was positive or negative in the context of the game being played. Using this reward as feedback, the agent tries to figure out how to modify its existing policy in order to obtain better rewards in the future. So anyway, here is the structure, how it sees. We take a state of our current agent. We take an action according to our state, and after action we obtain our reward. And when we do a step, we get all this state, reward, done with that or not done that, and so on. So next, I quote a detail. I have a details. Let me open my Brave. Here is a gym environment I'm trying to make, and here is the all the instructions about our landing agent. And anyway, I'm not going into details right now, but we know that we must land our agent in the center, and if we land it bad, we get a negative reward, and if we solve it and we simply land it correctly, we get a 200 points. It's quite not necessary to know our details because our agent should learn everything of this. So if you want, you can read this. This code provides enough details about the action and state space. And also, I observed that there is some random wind in the environment that influences the direction of the ship. So it's some kind of noise. And here is our 4 action space discrete, which we can use. It's something similar to cardball. So when we send a 0, we do nothing. When we send 1, we fire left engine. When we send 2, we fire down engine. And when we send 3, we fire right engine. And these actions corresponds here. So now let's go ahead, and I already implemented this random agent, as you can see, interacting with the environment. So I can simply run this and you'll see how it works. You can by yourself create a random.py script, copy this code, and simply you can test if you installed everything correctly and if it's work for you. Because I do not recommend to move forward to reinforcement learning if environment doesn't work for you, because you can find a mistake later. So this creates an environment, object environment, somewhere here, for the LunarLander v2 gym scenario, where our player spawns at the top of the screen and has to score in an empty goal to the right side. If you see a spaceship on your screen taking random actions in the game, congratulations, let's run this. As you can see, it's really fast. Import time, I'll make it a little slower. Time.sleep and 0.1. Let's run it. Sorry, import time. Yeah, it's too slow right now. Yeah, as you can see, right now it's random. And if you see a spaceship on your screen taking random actions in the game, congratulations, everything is set up correctly, and we can start implementing the Proximal Policy Optimization algorithm, actually. So next, it's called Ppo. The Ppo algorithm was introduced by the OpenAI team in 2017, but of course, you probably should know this already. And here's the paper of it. And it quickly became one of the most popular reinforcement learning methods that pushed all other reinforcement learning methods at the moment aside. Ppo involves collecting a small batch of experiences interacting with the environment and using that batch to update its decision-making policy. Once the policy is updated with that batch, the experiences are thrown away and new batch is collected with the newly updated policy. This is the reason why it is an on-policy learning approach, where the experience samples collected are only useful for updating the current policy. So the main idea is that After an update, the new policy should be not too far from the old policy. For that, Ppo uses clipping to avoid too large updates. This leads to less variance in trading at the cost of some bias, but ensures smoother trading and also makes sure that agent does not go down to an uncoverable path of taking senseless actions. So let's go ahead and break down our agent into more details and see how it defines and updates its policy. So actually, I'll open my original code, I'll close this, and here is my full implementation of my code. So right now I'll begin with the structure and I'll show you a few slides, images, doesn't matter. Here is a first one. As you can see, the Ppo uses the actor-critic approach for the agent. This means that it uses two models, one called the actor and the other called the critic. The actor model performs the tasks of learning what action to take under a particular observed state of the environment. In LunarLander v2 case, it takes 8 values list of the game as input, which represents the current state of our rocket, and gives a particular action what engine to fire as output. As you can see, we take an input, then goes our trainable network, and we get an action probabilities of softmax. And it's simply, we choose the best of these probabilities. And if we look at my code of actor model, here it is. And as you can see, I use a optimizer, it's Adam. And here is the softmax. Here is action space, which is 4 in this case. And I use a 3-layer deep neural network, and so on. So here we are first defining the input shape for our neural network. Here, input shape. For our neural network, which is the shape of our environment action space, which is the total number of possible actions available in current environment and will be the total number of output nodes of the neural net. I'm using simple 3 deep layer neural network, as I said, with the following neurons with the 512, 256, and 64, and the last layer is the classification layer with the softmax activation function added on top of just trainable future extractor layers. This way our agent will learn to predict the correct actions. Everything is combined and compiled with the custom Ppo laws. This fall, and this is where the magic happens. And this is the most important part of Proximal Policy Optimization algorithm. So let's first understand this loss function. But first I should say that I'll just not go into details, because for me it's also quite hard to understand everything. Here comes the probabilities, and all probability of actions indicate the policy that is defined by our actor neural network model. By training this model, we want to improve these probabilities so that it gives us a better and better actions over time. Now, a major problem is in some reinforcement learning approaches is that once our model adopts a bad policy, it only takes a bad actions in the game. So we are unable to generate any good actions from there on, leading us down on uncoverable path in training. Ppo tries to address this by only making a small updates to the model in an update step, thereby stabilizing the training process. Following Ppo laws code can be explained in four sentences. I'll try to explain them. So here is our state probabilities, and there is our previous old state probabilities. So simply here comes probabilities from state, here comes from next states. So Ppo uses our ratio between the newly updated policy and the old policy in the update step. Computationally, it's easier to represent this in logarithmic form. As you can see, here is log, and we calculate the exponent of this. Using the ratio, we can decide how much of change in policy we are willing to tolerate. Hence, we use a clipping parameter, entropy loss clipping, to ensure we only make the maximum % change to our policy at a time. So, and paper suggests using the value of 0.2. This means that we allow to improve our agent for 20%. For example, if we need to change by 1, we in some kind of direction of actions, we only gonna do a change in 0.2. So this will be a small improvement, and we check everything next in the next step. And we do this a lot of steps. So this is why our PPO loss agent takes more time to train, but it usually trains better. So actor loss is calculating by simply getting a negative mean of element-wise minimum value of P1 and P2. I won't explain everything in details, as I said, and adding an entropy term is optimal, but it encourages our actor following entropy. This encourages our actor model to explore different policies, and the degree to which we want to experiment can be controlled by an entropy beta parameter. Entropy loss. Following. So you should try everything, experiment by yourself. Next is the critic. So what is about critic? So we send the action predicted by an actor to our environment and observe what happens in the game. If something positive happens as a result of our action, like landing a spaceship, when the environment sends back a positive response in the form of reward, but if our spaceship falls, we receive a negative reward. These rewards are taken by the training our critic model. As you can see, everything the same, except that the output is one neuron, which gives us value, a real number. So the main role of the critic model is to learn to evaluate if the action taken by an actor led our environment to be in a better state or not, and give its feedback to the actor. Critic outputs a real number indicating a rating of the action taken in the previous state. By comparing this rating obtained from the critic, and the actor can compare its current policy with a new policy and decide how it wants to improve itself to take better actions. Same as with the actor, I implemented it, and we can check it here. And this is not necessary for custom PPO loss function, but we'll talk about this later. So as you can see, the structure of this critic neural network is almost the same as the actor, but you can change it, test with this, with what structure is best for you. You don't need to use the same structure as the actor. The only major difference being the final layer of the critic output a real number, as I said. Hence the activation used is none. Here we could use 10H also, but not softmax, since we do not need a probability distribution here like with the actor. Same as in actor, I use a custom PPO2 critic function where clipping is used to avoid too large updates. I can't give you a brief explanation about this custom function because I couldn't find a paper where it would be explained properly, so it's up to you if you believe me or not. Now, an important step in the Ppo algorithm is to run through this entire loop with the two models for a fixed number of steps known as Ppo steps. So essentially we are interacting with our environment for a certain number of steps and collecting the states, actions, rewards, and etc., which we will use for training. But before training, I need to process our rewards that our model could learn from. So I use a generalized advanced estimation function. Advantage can be defined as a way to measure how much better off we can be by taking a particular action when we are in a particular state. We want to use the rewards that we collect at each time step and calculate how much of an advantage we were able to obtain by taking the action that we took. So if we took a good action, we want to calculate how much better off we were by taking that action. We want to do that not only in the short run, but also over a long period of time. This way, even if we do not immediately score a goal in the next step, we will look at few time steps after that action into the longer future to see if we received a better reward. If you were in reinforcement learning for a while, you probably faced a discounted episode reward strategy. That's one of the simplest and most used strategies to process rewards, but there is known method called generalized advantage estimation, and I give a link to a paper in my text version tutorial, but I'm not opening here and not explaining because it's very hard. It's a hard math, which I can't explain step by step, which I'll use to get better results. So this is the generalized advantage estimation algorithm implemented in our code here. If you're interested, you can uncomment this line and check what is your results, how it looks when it plots in Matplotlib, but I'm not doing this right now. I want to save my time because I don't have a lot of it. Let's take a look at how this algorithm works using the batch of experiences we have collected. Here, dunce is used because if the game is over, we are not interested in what our next value will be. We simply use our last received reward without discount. Next is gamma, which is nothing but a constant known as discount factor in order to reduce the value of the future state, since we want to emphasize more on the current state than a future state. We can consider this getting a reward earlier is more valuable than rewarding in the future. Hence, we discount future rewards so that we can put more value to present a good action. Lambda is a smoothing parameter used for reducing the variance in training, which makes it more stable. This gives us the advantage of taking an action both in the short term and in the long term. Of course, I try to play with it, but I think everything depends on the environment where you do this. And in the last step here, we simply are normalizing the results and divide it by standard deviation. It's normally used in discounted reward and all other reward systems. Actually, it's hard to understand everything in the smallest details. I'm not sure by myself if I understand this reward system correctly. So if you want to get details of it, I recommend reading the paper. So just like that. So moving forward, now we can finally start the module training. For this, I use a mostly known the fit function of Keras, and I called everything in replay function. We can call it training function, but I use it as replay because in the past I used the same function. You should now be able to see on your screen the model taking different actions and collecting rewards from the environment when you run simply this following code of mine. And at the beginning of the training process, the actions might seem fairly random as the randomly initialized model is exploring the game environment. So, as an example, right now I'm not showing this, but for the first 7 episodes, I extracted rewards and advantages that we use to train our model. I tried to save the plot to show you if you don't have time to do that, and you can see that what I show you right now. These are the rewards orange and advantage is in a blue color, and you might see that when our agent loses, the advantage drops significantly. So what does it mean? So here is 120 steps, around 120 steps is one episode, and when our agent loses, it means it crashes to the ground, it hits this bad results of 1 month. At the bottom of this chart is minus 140, around minus 100. And as you can see, advantage drops very similar to it, and this advantage is used to train our actor. And when it lands correctly, spike will be to up because it would receive 200 points in positive reward. So that's it. It's a quick review. So right now we can try everything together, now that we have our actor and critic model defined, cover rewards and training parts, we can use them to interact with the gym environment for a fixed number of steps and collect our experience. So actually, I'm not running right now a training process, how it looks, but I can show you how it looks in a test environment, because actually it's quite the same. Oh, before that, I can show you how my training chart looks like before showing the results. And here is a run function, which is used to train on episodes. So it simply trains every episode, and here is a run on batch, and this is recommended for Proximal Policy Optimization, and it simply has some kind of training memory, and when it fills up, we call a training function to use that memory to train our PPO, and this is the while loop, and that's it. So I use this function to train a LunarLander v2 agent for 4,000 of steps, and from the following chart you can see that it took only 1,000 steps to start getting maximum rewards. This is the amazing results. Actually, I had to do a lot of hard work, a lot of hard coding and debugging to achieve this kind of code, because at first I tried to Google the GitHub for some working code or something, good explanations how everything works and so on, but I couldn't. I simply couldn't. Then I started reading paper, getting into details and so on. I actually lost a lot of my expensive time to create this working proximal policy agent from scratch. And actually, I'm giving my code for free to you guys to use it wherever you want. You just need to mention me in your project and so on, and it's free. It's free for you, and all my future code will be free. At least I think so. And except if I'll have some kind of investors, maybe someday. Maybe I won't have an open source code, but right now I give everything for free. So actually now I can run a test, and let's see how my agent works. And here I load my agent. As you can see, I have my saved actor and critic models. Here's my random agent, and that's it. Let's see how it looks. Wait a moment, some kind of problem. So I had an error here with random. I couldn't find what's the problem, but the reason was that I was using random.py instead of random agent.py because it was understanding it as library and couldn't use it as library. So fuck it. I damn it. I hate this stuff like this. But anyway, now it's working and I can show you everything how I'm testing it. So let's run. And you should probably see in a moment. And as you can see, here's the score of it. And that's it. Whatever else you need to know. It's working and you can train it, of course. And of course, I have here our multi-process training, and I'll maybe explain it later in next tutorial, but because right now it would be too long tutorial to explain. But maybe I'll find time to do this next time, and I recommend to use this training method. It works much faster because we are playing with an 8. In this case, we are playing 8 environments in parallel, and it trains much faster. It's easier to collect the training history for it. So yeah, that's it. And now I hope this tutorial will give you a good idea of the most popular Ppo algorithm. I tried to write my code as simple and understandable that every one of you could move on it and implement whatever discrete environment you want. Also, I implemented multi-processing training as I said right now, and that's it. So you can use my code to solve even more complicated games. I just chose the LunarLander for my experience, simply to use it to test if my code works correctly. So that's all for this tutorial. In the next part, as I said, I'll try to implement continuous proximal policy optimization algorithm that could solve more difficult games like bipedal walker v3. And this is the robot, 2 legs robot, which needs a continuous action space, and I'll try to explain this. What does it mean? So that's it for this tutorial. I hope this was useful for you and you would use my code and whatever you need to increase your knowledge about proximal policy optimization and reinforcement learning. And that's it for now, and see you in the next time. See you later, guys and girls. So goodbye.